Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Senyola Oluwa and I've been guiding you through the chemistry course. In this particular lesson, we'll be looking at metals and their compounds. That's the second part. Yes, that's part 2. Metals and their compounds, part 2. And this particular one will look at transition elements. We'll consider the properties of transition elements. Then we'll talk about iron and its compound, copper and its compound, zinc and its compound, and then we'll consider alloys. Alright, let's begin. When we say transition elements, what comes to mind? Well, we have our periodic table, and in our periodic table, we've been drawing periodic table earlier in this lessons, and we have drawn periodic table of first 20 elements, and we don't see something like transition metals. But in this time around, we're talking about transition elements. Well, transition elements occupy the D block of our configuration table, our magnetic configuration table. They occupy the D block. So when you see them in the D block, talk about the D block. Of course, that's after the S, the P, then we come to the D, and then the F. In the F block, we have the lanthanide and the actinides. The lanthanides and the actinides, but the transition elements stay in the D block. So, what are these transition elements? I know you've heard about many of them, like scandium, like zinc, iron. I know you're very familiar with those ones. So, second to the iron, the zinc, the uranium. Yes. So, they are all transition elements. We'll be looking at the properties of transition elements. What are the properties of these transition elements? On your screen about now, there will be a diagram showing the periodic table, yes, and the location of the elements in the periodic table. The properties of the elements include the fact that they are all metals. They have high melting points and boiling points. Of course, like normal metals, they do have high melting and boiling points. They ionize by loss of electrons. Some of them do exhibit. That's one of the reasons why we call them. The main reason why we call them transition elements. Now, that's what I'm about to tell you. They do exhibit a change of. They exhibit more than one ionization power. That is, they can actually be more than one. They can actually have more than a fixed number of valence electrons. I think that's the best way to put it. More than a fixed number of valence electrons. They can control what happens in the arrangement of their shells. We'll see on the screen about now. You see the arrangement of the shells of the first 10 of the transition metals. You see scandium having 1 in the D block, and titanium having 2 in the D block, vanadium having 3 in the D block, manganese and chromium having 5 instead of 4, and it takes 1 to the S block. And they make alterations. They have the capacity to alter their arrangement, of their electrons in the shells. This is one of the major reasons why they are described as transition elements. And usually they are solids, most of them are solids, and they do have colors. They are colored elements, they are colored substances. Of course, on the screen about now as well, you'll be seeing the colors exhibited by the different materials. There are different ions. Of course, yes, a paper table that shows colors, and also it shows their atomic number, their melting points, and their ionizing radius. That's the ionic atom radius. If you look through it, you notice that zinc is colorless, scandium is also colorless, but you have titanium, which is brown, vanadium, which is purple, chromium, which is blue, manganese pink, iron, which is green, cobalt, which is pink, nickel, which is pink, green, and copper, which happens to be blue. Another good thing about them is their chemical reactivity. Their chemical reactivity, they react in unique ways. The number of electrons in the outermost shells of the element is supposed to determine how the element would react. Well, because of the nature of their existence, that they can control how many electrons will be in each of their magnetic axis, that is the number of spins that they do have. They can control it. They can decide that instead of filling an 4s, instead of filling 4s, they can decide to fill 3d first. They can decide to take an electron from here to fill here. So because of that nature of theirs, they do exhibit multiple valent structures. They do have more than one particular valency, and this also affects their reactions. This affects their reactions. They simply choose the one that is convenient for them. And also, they are generally reducing agents. They do take part in redox reactions. Yes, they do form complex ions. They do form complex ions, and even their ions have their own colors. On your screen about now, you see the colors of their ions. Many of them are used as catalysts, and they are used as catalysts in different reactions, in different chemical reactions. They will be there to ensure that a particular reaction take place. And one of such reactions is the hydrogenation of oil into margarine. Hydrogenation of oil into margarine. We use vanadium as a catalyst. We have very many substances, so very many experiments where we find them being used as catalysts. Alright, we've spoken about transition elements and their properties. In a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson so far. Please do well by answering them, and when we come back, we'll continue with iron and its compound. Welcome back. So we talked about transition elements. Now we want to look at iron and its compound. Iron and its compound. If you look here and there, you see iron existing all around us. Our television sets, hangers, tables, desks. We have iron being used to make almost everything around us. Well, iron itself is naturally abundant in nature. It exists in different forms, in form of iron rock, iron stone, most of which are excavated or extruded from the ground, from the earth source, and are being processed. The process of manufacturing iron involves a lot of things. It involves, depending on what type of iron that is desired to be produced. First, it involves you bringing out the metal, the rock, and everything, then cleaning it, removing unwanted materials. After removing unwanted particles, then you add some chemicals to it and you heat it together. Then we engage in what is called the roasting of the ore. The roasting of the ore. The iron raw ore will be roasted, and when it is roasted, it will form complex forms of oxides. These complex forms of oxide will be further processed in the lab, in the industry by different kinds of chemicals, treatments. After this treatment, we have our iron ore, our iron that is separated. We have three types of iron that we do work with, that we can harvest. We can harness the pig iron, which is actually the dirty iron, the one that has a lot of different kinds of impurity, but it is relatively stronger compared to wrought iron. Wrought iron is a purer form of iron, though it still contains some level of impurity. And then we also have the steel, or the carbonated ions. Now, steels contain impurities just like others, only that the level of impurity in steel is more of the carbons and some other additives. We have different types of steels. We have mild steel, we have high carbon steel, we have high speed steel, we have moderate carbon steel, we have different kinds of steels, and we also have alloyed steels. All this type of steels are all selected based on the type of properties, based on kind of chemicals that have been added to it, the additives that have been added to this particular ion. Of course, steel is an alloy, so when we get to alloys, we'll talk more about that. All right, let's look at iron. When iron has been processed and it is clean, it comes out clean. It has a silver solid, it has a silvery appearance with luster. It has a relative density of 7.9, and it is very malleable and ductile. It has a very high tensile strength. It has a melting point of about 1530 degrees Celsius. That's like, wow, yeah, that's iron for you. And it is a very good conductor of heat and electricity. It also has a special property. It is magnetic in nature. It is magnetic in nature. When you roast iron in the air, it tends to form different kinds of compounds. But when you allow iron to stay in atmosphere, your pure iron, if you leave it in an atmosphere, of course, you discover that your iron rusts. Yes, the iron rusts. What simply happens is that it reacts with the oxygen in the air and water vapor in the air. And when it reacts with water vapor and oxygen in the air, it will form the iron 3 oxide, which is actually an anide, which is actually an hygroscopic substance. It needs a certain amount of water of crystallization for it to form its own crystals. So the water vapor it absorbs that helps it to form that iron 3 would also become the water of crystallization that will be found in the iron. Iron reacts with steam. Red hot iron reacts with steam, and it produces iron 2 diiron 3 oxide. Iron 2 diiron 3 oxide. That is this particular Fe3O4. Iron 2 diiron 3 oxide. Now this particular oxide also is a very reversible reaction, so it can go either way, forward or backward. Also, iron reacts with other non-metals such as chlorine, as fluorine, as sulfur, depending on the nature. Just the same way it reacts with oxygen, it reacts with other non-metals. And iron, of course, like every other metal, it has the acidic property. It reacts with acids to liberate hydrogen. Of course, I don't need to tell us the application, the uses of iron any longer, because we can tell very many uses of iron in the production of our steels, in chemical reaction. It is used as catalyst. It is used for very many purposes. In fact, it is one of the most used substances by humans, especially in construction, in different fields of life, in all fields of life. Of course, we all know that our drinks, our blood tonics, also contain iron. Yes, it is because of the love for our oxygen possessed by iron. That is why the hemoglobin actually also contain a certain quantity of iron 2. All right. Well, we have different types of iron. We have iron 2, we have iron 3, and it has been observed that iron 2 oxide is not so stable. The iron 2 oxide is not stable. Every time that iron is existing in the iron 2 oxide and it is exposed to air, it quickly transforms into iron 3 oxide. Iron 2 oxide has a greenish coloration, a greenish color. Of course, we are told that almost all the transition metals have colors. Iron 2 exists in a greenish color, but when it is exposed to air, it turns reddish brown, which is the color for iron 3. For the iron 3, iron 3 is brownish, reddish brown in coloration. All right. The reactions that iron do exhibit, we have the nature's states of ions. We have iron 3 oxide. Of course, I've told you about iron 2 oxide, which is not stable. It quickly goes back to iron 3. Iron 3 oxide can be produced by the decomposition of iron tetraoxosulfate 6. When you decompose iron tetraoxosulfate 6 by heating it, you produce iron 2 oxide, sulfur 4 oxide, and sulfur 6 oxide. Also, when you react iron with water, when you react iron directly with water, it liberates hydrogen to produce iron 3 oxide. So iron 3 oxide is the most stable form of ion that we can have around. That's why most of the time when we see particular things, what we see around us is when you talk about iron, you see it is having a brownish color, because that is the nature in which iron likes to exist. Of course, iron also can be used since they are colored items. Many of these transition metals are used as dyes. They are used as dyes for applying color to our clothes and other things. Yes, let's look at further for more compounds of iron. We talk about the iron 3 chloride. Iron 3 chloride. Iron 3 chloride is formed by reacting iron with hydrochloric acid, and to produce, it will liberate hydrogen and produce the iron 2 chloride. It will liberate hydrogen and produce the iron 2 chloride. Of course, we know that every acid that any metal reacts with, there is a chance that they will liberate hydrogen, except the metal is lower than hydrogen in the electrochemical series. Also, we can produce iron 3 chloride. Iron 3 chloride can be produced when iron is burnt in the presence of excess chlorine. When iron is burnt in the presence of excess chlorine, it produces iron 3 chloride. Also, we can produce iron. There is also the iron tetraoxosulfate, which we talked about earlier, that was used to produce iron 3 oxide rather. Iron tetraoxosulfate 6 can be produced by reacting iron with tetraoxosulfate 6 acid, and we have the liberation of hydrogen, and we have the iron tetraoxosulfate 6 salt. Also, there can be the iron 3, there is the iron 2 tetraoxosulfate 6 salt. There is also the iron 3 tetraoxosulfate 6 salt. This salt can be decomposed, and when it is decomposed, it produces iron 3 oxide and the sulfur 6 oxide. When it is decomposed, it produces iron 3 oxide and sulfur 6 oxides. All these forms of iron, all these different natures of iron have benefits which they do give to us. On your screen, in a few seconds on your screen, you'll see different metals, their colors. And all right, let's talk about copper and its compounds. When we talk about copper and its compounds, copper can be sourced from the earth as well, just like other minerals. It exists not in its free state, of course. It exists in combination with iron, with sulfur, and other substances. The most abundant forms of copper that can be sourced is always connected to sulfur. So whenever we want to whenever we want to purify copper from what is being extracted from the ground, that is the minerals, we always roast copper in the presence of air. We roast copper in the presence of air. This roasting leads to the separation of the bonds, and you have copper sulfide at the end of the whole process. Then you burn this copper sulfide also again in the presence of excess air. When you burn the copper sulfide in the presence of excess air, the sulfur would stick to the oxygen, and copper, pure copper, would be formed. All right. Let's look at some of the properties of copper. Now, that's the pure copper. Copper is physically, it is red, it's soft. It's a soft metal. It has a red appearance, a red solid with luster. It has a relative density of 8.95. It is very malleable, very ductile. That's one of the reasons why we can easily process it into wires and use it in our electric cables. It is it has a very high tensile strength, a melting point of about 1080 degrees Celsius, and it is an excellent conductor of electricity and heat. It is an excellent conductor of electricity and heat, transferring up to about 98.6% of all the electricity that is being supplied to it. So this is one of the features that makes us use copper for our cabling system. Alright, let's consider the chemical reactions that copper do exhibit. Copper is quite low on the electrochemical series, so it does not react so much. It reacts with oxygen to form copper oxide. It also reacts with acids. And reacts like a weak metal, of course. It can react with hydrochloric acid and displace hydrogen in the hydrochloric acid. It can displace hydrogen in the nitric acid, just the same way it displaces hydrogen in the tetrasulfate acid to produce copper tetrasulfate 6, water, and sulfur 4 oxide. Okay, let's look at the oxides of copper. The oxides of copper. Copper has 2 oxides, that's copper 1 oxide and copper 2 oxide. Copper 1 oxide can react with any acids, of course, to liberate steam. Of course, it can give off steam, but even at that, when it reacts, it will produce the copper salt, this copper salt, and it will also produce copper itself. It could produce copper itself because of the nature of the element, the substance. But if you use copper 2 oxide to react this same acid, it will produce just the copper salt and water. Well, copper 2 oxide also can be burnt, it can be displaced. The copper can be displaced even by hydrogen. If you use water, if you use heat copper 2 oxide in the presence of hydrogen gas, you have copper and water produced. But here we are having copper 2 oxide reacted with carbon 4 oxide, which produces copper and liberates carbon 2 oxide, which produces copper and liberates carbon 4 oxide. We have many other reactions in which copper takes place in, but very, very importantly is the production of the basic substance of copper. The basic substance of copper. Copper base is not soluble in water. Yes, the base of copper is not soluble in water, so you can precipitize copper in a particular solution by reacting the solution with sodium chloride, and the chloride, sodium hydroxide rather, the hydroxyl form of it would react with the copper to produce copper hydroxide, which is actually an insoluble solid in water. Alright, so these are basically the substances that come out of copper. We also have copper chloride, copper nitrate. All of these are formed by reacting their acids with copper. Copper is of very, very great importance, especially when it comes to the transmission of heat and electricity. Transmission of heat and electricity. That's why we do use our copper the most, and it is quite abundant in nature. Alright, let's take a quick look at the last of the elements, which is zinc and its compound. When we're talking about zinc, zinc has a few different things that makes it unique among other transition metals. I'll mention 3 things. The first thing is the fact that it only maintains as much as possible 1 oxidation point, which is +2. That's the standard oxidation point of zinc. It maintains a +2 in all its reactions. You don't see zinc 1, you don't see zinc 2, zinc 4 or zinc 3. It only maintains that +2 in all its reactions. Apart from that, it does not act as a catalyst in any reaction. Zinc just stays numb when it's not working. It either takes part in the reaction or doesn't do anything. It does not hasten any reaction. And thirdly, it does not have a color. It does not have an ionic color. It is colorless, either in the ionic state or in the atomic state. Alright, let's consider the zinc as a substance. It has a bluish white solid, so that is its natural color. It does not alter its color for any other reason. It has a lustrum, it has a relative density of 7.1. It's malleable and ductile, high tensile strength, and a melting point of 419 degrees Celsius. A good conductor of electricity and heat. Our chemical properties include the fact that zinc bonds in air, it reacts with oxygen and produces zinc 2 oxide, or simply called zinc oxide. And when it is burnt, when hot steam is passed over the hot zinc, red hot zinc, it liberates hydrogen and creates zinc oxide as well. It reacts with chlorine and other non-metals in an addition reaction to form their salts. It also reacts with acids, as of course it is a metal. It reacts with acids and when it reacts with acids, it liberates water, and of course sometimes it also gives off some gases because it is not a strong metal, just like other non-strong metals like iron and the others do. Aside that, it also reacts with bases. Yes, it reacts with bases because it is an amphoteric oxide. Zinc is amphoteric in nature, so when it reacts with bases, it joins them to form stronger bases. Okay, let's take a look at the oxides of zinc, or compounds of zinc. We have zinc oxide, which is produced by burning zinc in presence of air. Zinc is used for a couple of purposes. Zinc as an element is used in the galvanization of iron. Yes, it is used to galvanize iron. It is also used to make alloys of different kinds. Examples of alloys that are made of zinc include brass and bronze. They contain large quantities of zinc. They are also used in making dry cells, dry batteries that we use in our phones. Sorry, not in our phones, in our flashlights and other substances like that. We use zinc in the making. Yeah, zinc oxide, of course, it finds its use in pigment making, in plant and paint making. It is one of the pigments used in paint making. It is a filler for rubber. Yes, it's a filler for rubber in the vulcanization of rubber. It helps in the vulcanization of rubber, and it's also used in making of some cosmetic powders. Yes, some cosmetic powders, because zinc is actually good for the skin. It has a good, it has a soothing effect on the skin. All right. Well, we'll go to talk about other form of existence of zinc. We see zinc hydroxide. Zinc hydroxide is amphoteric in nature. It reacts with acids to produce salts, water, and liberate gases where necessary. It also reacts with bases to formulate stronger bases, complex bases. Zinc reacts with hydrochloric acid to liberate hydrogen, of course, and it forms a salt known as the zinc tetraoxosulfate 6 salt. This salt is actually deliquent. It is a deliquent salt, and it requires a water of crystallization of about 7 molecules water of crystallization. With this 7 molecules of water of crystallization, this particular compound is ready for work. This compound can be used in the treatment of certain skin diseases. It is used in the making of paints, and it's also used in the making of eye drops, eye lotion. Okay, let's talk about the zinc trioxonitrate. The zinc trioxonitrate is produced by boiling the zinc oxide in trioxonitrate 5 acid, or the concentrated one. Yes, and it will produce the zinc trioxonitrate 5 and water. Alright, we've said a lot about zinc and its compound. Let's quickly look at other alloys, and we'll talk about what alloys are, and other classes would look at other things. So what is an alloy? When we're thinking about the word alloy, an alloy is simply a particular metal or a substance, a compound that contains 2 or more metals put together in such a way that it can enhance the features or the characteristics of the metal. The new product is designed such that it can create something that is better than the other products. Let me give an example. Maybe that will shed more light on it. Let's talk about steel. Yes, I told you the other time when I was talking, I said steel, and I said I'll shed more light on it when we get to alloys. When we talk about steel, steel is an alloy. It's simply an alloy of iron and carbon. It's an alloy of iron and carbon. Now, it does not mean that all steel contains strictly iron and carbon. Some other steels, like stainless steel, contain other elements as chromium, as titanium, other substances like that. These elements, these extra elements are added with the intent of increasing or improving certain qualities of these metals. For example, iron is hard, but iron is not as hard as carbon. Now, to enhance the strength of a metal, it is good that that metal be alloyed with, to enhance the strength of iron rather, it is good that the iron be alloyed using carbon. When you mix iron and carbon together, it forms a stronger and a more reliable material known as steel. Now, that steel again can also be further enhanced. You can add compounds like titanium to improve the ability to withstand heat. You can add compounds like chromium to improve the ability of it to withstand corrosion and scratch. It becomes anti-scratch, anti-corrosion. And then you see coming up with the design that we are drafting out is something of that of the stainless steel. And then you see many other different reagents can be added to it. You want to put a particular color in your steel. You want your steel not to look like the normal conventional gray it is appearing. You can take a transition metal and add it to it, stain it with a particular transition metal that can give you the coloration that you desire. You want your stainless steel to become even more electrical inclined, that is, can transmit electricity even at a higher, faster rate. You can alloy your stainless steel with your copper. It also enhances transmission of electricity. You can alloy your stainless steel with tin. It prevents scratching. So you see many different compounds being put together to form alloys. But very soon, in a few seconds, the table will be displayed on your screen showing different alloys and their composition by mass. Okay, there you have bronze, you have silver, you have bronze, you have brass, you have quadrillium, steel, stainless steel, and the others. So all this, if you take your time to look through the advantages and disadvantages of the advantages rather that have been gotten from alloying these particular compounds using this method. Of course, you see that duralumin is a very light and very strong form of aluminium. It is very light, very strong, so it can be used in the construction of aircraft, vehicles, and other machinery that require light weight. So we see very many advantages that come from alloying of substances. Alright, I haven't spoken about so many things in this topic on metals and their properties and their compounds. We would like to take a break about now, and some questions will be asked of you in this segment. You are required to answer them. We want to know what you've understood, what you've learned in this lesson. And if any of the problems, any of the questions seem to be too difficult, you can go over the video one more time for clarification. Thank you.